Good. All right. Give yourself 2 points for that one. Okay. Guys, net force is what causes acceleration, right? But given the fact that you got multiple forces acting on you, like in this case, this guy is being pushed in this direction. The weight is pulling him down. There's a retarding force acting on him. Retarding force is not a force that turns you into a retard. It's just retarding your progress in this one. Okay, so when you have multiple forces acting on you, what's the meaning of a net force? Because net force is what causes acceleration. Real life cases like this one.
Chopping down a tree clean through by hand is a thing of the past. Pulling down a 30-foot evergreen with a tractor makes sense.
So the tractor pulls it this way. The roots will pull it in the opposite direction. The tree topples over.
But not with a 10-foot rope.
So when you have like multiple forces acting on a mass just like that, what's the meaning of a net force? What do we mean by it? Because we've been talking about net force nonstop for the past 2 weeks almost. This net force is what causes acceleration. So what's the net force if you got like two forces acting on a mass? Somebody pulling on this mass to the right, the other guy's pulling on the mass to the left. Forces are not the same, so it's an unbalanced system. So what's the meaning of a net force? Net force means the sum total of all forces acting on a system. It's the sum total of all forces acting on a system. Sum total, what does it mean? Does it mean that we add them up? Well, you add them up, it's going to give you 45 pounds. What good is that going to do? All right. Or is it more like the way you would think it should be, which is one person pulling on it this way, the other person is pulling on it in the opposite direction? So is it possible that the net force is 5 instead of 45? So all of a sudden, you notice that the direction matters. So we have to assign directions to it. All right. To the right, it's going to be positive. To the left, it's going to be negative. So the net force is the summation of all the forces acting on the system. This is sigma. That's the summation sign. Net force is the summation of all the forces acting on a system along the x direction. That's your x direction. That's your y direction. So net force is going to be responsible for the acceleration along the x direction. That's what it means. So you sum up the forces. F1 is going to be positive. F2 is going to be negative. Then the numbers is going to give you 5 pounds. That's it. All right. So meaning of the net force is literally you're summing up the forces. Direction is going to matter. So when you sum things up, positives, negatives, it could be subtractions, it could be additions, and so forth. That's it.
The dummy contorts and stretches from the immense force. In only seconds, its arm is wrenched off by one of the aircraft, while the other plane drags the broken torso down the runway. Stanley knows the same thing could happen to him, but he's determined not to back out.
We'll make it. We're gonna make it. Okay.
Like that?
It's time. The pilots gun the engines. The ropes pull tight as the two Cessnas try to take off at the same time, at the same speed, in opposite directions. Their tachometers have already risen to 1,500 revolutions per minute. Remember, the goal is 2,400. Stanley braces against the tremendous force. Now, at 2,000 RPMs, nearly enough to take off. Grimaces as he fights to hold his ground. Barbara watches, terrified and helpless. The tachometers now read 2,200, more than enough power to take off. Stanley has only 200 RPMs to go. Then suddenly, he's pulled off balance. It looks like he's being overpowered, but somehow he summons all his physical and mental strength to stop the two planes from tearing him apart. Both engines are now revving at a fierce 2,300 RPMs, more than enough for them to be climbing into the sky. And finally, 2,400. Stanley has done it.
Wow, good for Stanley. All right, guys, what's the net force acting on him right now? Use the chat. What's the net force acting on him? All right, so the net force acting on him is 0. How do you know that the net force acting on him is 0?
Because they're equal forces pulling in opposite directions.
Oh, okay, that's awesome. Okay, every single person who wrote something so far, I'd give yourself 5 points. Give yourself 5 points for the explanation. That explanation, if this were a test question out of 2 points so far, you would say it's 0, and because the two equal forces in opposite directions, yeah, guys, that's an entire statement there is 1 point, no more than that. All right, and that's the sort of statement that is very questionable because it's more of an assumption that you're making. And I don't want any assumptions. I don't want anything that starts with I believe, I think, I feel. Net force acting on me 0 because complete that sentence and use physics. Don't use anything else. Make it factual statement. How do you know that the net force acting on me 0? You can't say that the forces are equal. You don't know that. You cannot feel the forces. You cannot see the forces. So that's not the way I would approach it. How do you know that the net force acting on me 0? Okay, so this brings us to the next point. A lot of problem solving in physics is conceptual, guys. You resort to math when you want to prove points because you're trying to generate numbers. This is the sort of stuff that you do. You look at it, you say, wait a minute, what's the net force acting on this guy? It's 0, but how do I know that? What's the definition of a net force? You have to go back to the definition. Physics is all about definitions and formulas. The formulas are summary statements. of the facts of the situation in reality. All right, so what is a net force doing? Net force causes acceleration. So this guy, is he accelerating? I'll get back to the definition of acceleration. Is he speeding up? No. Is he slowing down? No. Is he changing direction? No. So what's the net force? It's going to be zero because the acceleration is zero. I said nothing about the forces being equal. All right. Net force is zero. That's Newton's first law. So what happens when the net force is zero? The system is going to remain at rest. All right. In the absence of a net external force, the first law says the system retains its initial motion. All right. The object at rest is going to remain at rest. Object in motion is going to keep on moving in a straight line at a constant speed. This is an object at rest. The absence of a net external force is not an absence of a force. There are two forces acting on this guy. And these forces are so large that if I were to take his place, I would more than likely lose my arms. But the net force is zero, which means that the forces are in opposite directions and they add up to zero. They cancel each other out. When the forces cancel each other out, the canceling forces, it doesn't mean that there are no individual forces acting on the system. There are a tremendous amount of individual forces acting on the system.
Risen to 1,500.
There are net force acting on this guy now, of course. How do I know? Because he accelerated. He went from zero to something else. That's it. So that's what happens when one force is larger than the other one, in this case. So it's going to end up moving in the direction of the resultant force, the net force. If this airplane applies a force, which is about a pound more than the other one, it's going to accelerate this way. Now, it creates a problem, obviously, because if they apply exactly the same force on this guy, what's going to happen is he can lose his balance. If he does, he can lose his arms, potentially lose his life.
Revolutions per minute. Remember,
The car breaks down, so two people are pushing on the car, right? This is problem number 5 from the handout. So there are two forces acting on the car. Two people are pushing on the car. Right? So there's a backward force opposing the motion. That's friction. Okay, the first thing we do is we do force diagrams. Okay, some that you guys will have to get used to. All right, so this would be the center of mass. It's usually a dot point. I kind of make it look like a ball for whatever the reason. It's my personal preference. So that would be center of mass. So the forces will be applied to the center of mass in this case. Two people are pushing against it. So one person is applying that much force. The second person is applying a little bit more in the forward direction. Lowercase f is the frictional force opposing the motion. Let me just stop this. Just want to make sure that we are recording. Okay, we are recording. All right, so the first thing is what's the net force in terms of newtons and pounds and the acceleration of the vehicle. And then if these people keep on pushing on this car for about 100 feet, how fast would the car be moving? All right, so only conversion is this 100 feet to meters. Okay, we're good. Net force is the summation of all forces along the x direction. So F1 is positive, F2 is positive, lowercase f is negative. So it's going to be 300 plus 400 minus 600. So it's going to be a 100 Newton force converted to pounds. It's going to be 22 pounds. Okay, so it's realistic. When two people push up against the car moves, but it doesn't move that fast. So the net force is going to be about 22 pounds. So you know the net force is what causes acceleration. You need to know the mass in this case. It's going to be 2,000 kilograms. That force is going to be 100 newtons. Mass is 2,000 kilograms. So it's going to give us 0.05 meters per second squared. A and B is straightforward. C is now we have to spill back to previously learned materials. All right, so we want to know how fast it's going to move in a certain distance. The applicable formulas are the ones that have acceleration in it. There's a presumption here. The presumption is that the acceleration is constant, or assumption, which may not be correct in this case, but we're looking for an estimate. So you know the initial speed, you know the distance. Okay, this formula uses this one. Or you can use the second one, but you need to determine the time from the first one. So that's kind of cumbersome. So the easiest one is the last one. Initial speed is 0, so that's the only number that I will plug in. Okay, only numbers I plug in my computations are zeros usually in algebra, nothing else. All right, so the final equation, A is going to be 0.05. 2 times 0.05, and then you need to have the distance, which is that's 30.5. Multiply square root, we're done. So we get a number in terms of meters per second. That's the same as about 4 miles per hour.
You're going to upload this video, right?
Oh yeah. All the videos get uploaded, obviously. So it's gonna get uploaded because, guys, I want you to just listen and participate. Don't worry about taking notes. During the lectures, you can always go back. Once you see the overlay, the big plan, when you're watching the videos, it gives you an idea of what to focus on. Because videos, you can slow down, you can take notes from the videos, but just get an understanding of what's going on. All right, so the car is fixed. This is a story about a car. Take it out for a test drive. So this is your drive force generated by the engine. This is the frictional force opposing the motion. And this is problem number 6. All right, so I do a force diagram. So drag force is in the forward direction, it's 1,000. Frictional force is still opposing the motion, so it's going to be 600. Mass of the car is still the same, it's 2,000. So what's the net force in terms of newtons and pounds? Newtons for physics, pounds is for us in the acceleration. And assuming that you're driving this car at 60 miles per hour for 30 seconds, how fast would the car be moving? So this car is already moving at 60. So net force forward is positive, backward is negative. 1,000 minus 600, it's getting 400. That's about 88 pounds, 90 pounds. Net force is what causes acceleration. So the net force is 400, mass is 2,000. It's going to be 0.2. Acceleration is reasonable. And what else? Okay, so the next question is, right, so how fast will the car be moving 30 seconds later? Right, that's the only formula you can use, assuming that the acceleration is constant. Right, you know the acceleration, you know the time, you know the initial speed. Initial speed is 60 miles per hour, so I forgot to include that. It's the same as 26.78 meters per second. All right, so this is 26.78 meters per second. All right, so let's move on to the numbers. Plus, acceleration is 0.02, it's right here. And time is going to be 30 seconds, right there. That's it. Multiply, add. You get a number, which is going to get expressed in terms of miles per hour. So it's 73.5 miles per hour, give and take. So within 30 seconds, you go from 60 to 73.5 miles per hour. All right, good. So quick review before we continue. All right, so what's inertia? Tendency to retain motion, or resistance to change in motion. Motion means velocity. It's a combination of speed and direction. All right, tendency to retain motion in the absence of a net external force. You may have forces, but make sure that the net force is zero. That's what it means. All right, so the inertia is also known as the Newton's first law, which is inertia. So where do you get the tendency from? You get it from your mass. So what's mass? Mass is the measured inertia or measure of inertia. All right, so mass is the same as measure of inertia. Proper unit is kilograms. In the United States, we use pounds. Newton's second law is the force law. Force acting on the mass is right here, cause an acceleration. Force acting on the mass cause an acceleration. All right, well, one of the things that you notice is force and acceleration is vectors, so they're pointing in the same direction. Proper unit is newtons. In the United States, we use pounds. All right, so you end up getting a conversion factor is 10 newtons roughly is 2.2 pounds. Next question, if something is speeding up, is there enough force acting on it? The answer to that question is yes, because it's accelerating. If it's accelerating, there's enough force acting on it. If something is slowing down, is there enough force acting on it? Yeah, slowing down is acceleration, so there's enough force acting on it. Something is moving on a curve at a constant speed, is there enough force acting on it? Yeah, it's moving at a constant speed, it's on a curve. Which means that the direction is changing, which means that it's accelerating. All right, Newton's third law seeks to answer the question of where these forces come from. Okay, so Newton said the forces come in pairs, which means that for every single action force, there's going to be an equal and opposite reaction force. Okay, so these forces come in pairs, and they're applied to two different masses, so they would never cancel. Action force is acting on the small mass, the reaction force is acting on the big mass. They have the same size, they got the same magnitudes. They're pointing in opposite directions. So that's it. All right, so how does that work in real life if there's a head-on collision between two vehicles, car and SUV? So which one experiences a larger impact force? Well, they experience the same impact force. Okay, so if that's the case, how come the car suffers the most damage? Well, the reason why the car is going to suffer the most damage is because while the forces are the same, smaller mass is going to accelerate more. So both vehicles will experience the same force. Smaller mass car is going to accelerate more, so it's going to suffer the most damage. So smaller the mass is, the bigger the acceleration is for a given external force. Taken to an extreme, you got a person in front of the train getting hit by the train, right? With 1 million pounds of force, 500,000 pounds of force. So does the person apply the same force back on the train? The answer to that question is yes. So if so, where's the evidence? This so happens, there's not much evidence that you'll be able to see because the train is very massive. Evidence the person applies the force back on the train is going to be in the form of acceleration. The acceleration of the train is going to be unnoticeably small, just a vibration, because the train is so much more massive than the person is. So what's the net force? It's the summation of all forces, or sum total of all forces acting in a system. All right, so add up the forces. These are vectors. Forces pointing towards the right, positive, left, negative. And that's it. Okay, so moving on with our story. So the car is fixed. You're taking the car out for a ride, and the car is going at 73.5 miles per hour. All right. While you're moving at that speed, you go easy on the accelerator at this point. All right, so notice that the accelerators, the drive force matches the frictional force on the car. So what's the net force? Forces are equal in opposite directions, acting on the same mass. Net force is going to be 0. All right, so if the net force is 0, what's the acceleration? It's going to be 0. So if that's the case, how fast do you think that the car is going to be moving 5 minutes from now? It's still going to be 73.5 miles per hour. All right, so when the car is going at 73.5 miles per hour, what if there's a massive engine failure? What if the engine just shuts off? What happens then? Does that ever happen in real life? You're driving at 75 miles per hour, 80 miles per hour, all of a sudden the engine shuts off. All right, it's just massive engine failure. Have you ever experienced something like that? All right, now, it's not supposed to happen. Who say yes? I'm just curious.
I did. Mark.
Okay, Mark, tell me what happened.
My dad was driving and he had a manual car and accidentally killed it.
Oh, okay. How fast were you guys going?
Not 70, but I don't know, 40.
Okay, that's not bad. So at least you had an experience of it. So that wasn't an engine failure. Your dad just messed things up.
Yeah, it just killed it.
It just killed it. All right, so mine happened like 20 years ago. This is not supposed to happen in real life. What I'm about to describe is very unusual. So I had a Ford Tempo. Okay, I bought it when I was in grad school because it was a really cheap stored car. And I wasn't taking care of it too well. Didn't care. It was a transportation device. And so evidently I forgot to change the oil for about 2 years. All right, so the engine started to smoke. Thank God it didn't burn. It was still working fine after that. Imagine that. I mean, that car was that good. Now the speedometer would go up to 90 miles per hour. The car would never go faster than 75. So I'm working at an art school, 2 campuses, one in Chicago, one in Schaumburg. They're 32 miles apart. And certain days I have to split my time between 2 campuses. So you have to just head back to Chicago in the afternoon. And then there's a bit of a traffic. So if you're lucky, you get there within an hour. So the lectures were like 1 hour apart. So one day I'm trying to make up time on a highway. So I'm going at 60, wasn't fast enough, go up to 65. I'm thinking, yeah, just go up to 70. How about 75, right? So you got up to 71, 72, 73, and then all of a sudden I'm trying to get up to 75, and it's not happening. The car started to shake violently, and then boom, the door pops open, so I just shut the door and then lock it up, and then I'm wrestling with the accelerator, and then these vibrations just started to get, the amplitude of the vibrations started to get larger and larger, and then boom, the engine cut off. So what happens when the engine cuts off? Okay, guys, you're on a highway going at almost 75 miles per hour, the engine cuts off. You're thinking it's not a big deal. You can just control the car and just pull it to the side, get off the road. Well, that was my initial reaction. Nope. Immediately, the steering wheel locked up on me. I'm thinking, this is not good. Just put the brakes on. There were no brakes. Emergency brakes. I evidently end up riding the car with the emergency brakes on, so I had no emergency brakes. So I'm going down in this missile and I had no control over it. And I'm thinking, oh shit, I'm going to die. Pure panic. And then I thought about it. Everyone is going to die one day, so I might as well take a couple of people with me, right? And then what happened? The car just slowed down to a stop. Took about 5,000 feet. All right, so I pulled to the side, and then I got out of the car, pushed the car out of the road, off the road. That was the extent of it. Serpentile belt evidently broke, which was supposed to be changed every other year. Okay, it's old technology. Again, just like the forgetting to change the oil, it was the same thing. It was a weird incident. All right, so Mark, your car, it's the same thing happened with your car, dad's car, right? It just slowed down to a stop on its own.
Yeah.
Yeah.
We had control the steering wheel, but yes.
Right. I'm surprised. Mine just locked up on me completely. I mean, even if you don't have brakes, it just comes to a stop. It slows down real fast, too, as if you put the brakes on. So it wasn't a big deal. All right, so this problem is inspired by a real-life story. So I thought about it. I was just curious about, it took probably about 1,000 feet for it to come to a stop. So how long would that take? So the force of friction is the only force acting on it. I was going around like 73.5 miles per hour, give and take. So a distance that it took like 1,000 feet. So the question is like, did it take like 5 seconds, 3 seconds, 10 seconds? What is it? It felt like it took forever. Pure panic. All right, so it goes from 73.5 to 0. All right, so what else do we have? I stated everything. All right, so I'm listing everything 73 miles per hour to 0 and within 1,000 feet. Force of friction, the amount of frictional force, as soon as the engine cut off, there was a lot more friction on it. I think I might have done some computations there. I'm getting this from somewhere. All right, so what's the net force? Newtons for physics, pounds for me. Acceleration, it's meters per second squared is good enough. I'm interested in the time in terms of seconds. All right, so what do we have? We need to have convergence. This is to meters per second. This is to meters. And pounds to newtons. That's what we need. All right, so the only one that we will have to do a conversion. Okay, so we know how to convert miles per hour to meters per second. All right, so we can just pull the number out of that one. Feet to meters, we've done it a number of times, so we can pull the number out of that one as well. All right, so pounds to newtons, we kind of alluded And we may have used it last week, but we need more practice with this one. So we have to go from pounds to newtons. Just remember, roughly 10 newtons is 2.2 pounds. All right, so that gives us that. All right, so I pulled up all the formulas that we may need. Okay, there's a repetition. I just didn't know how to delete that. So the net force, this is the easiest one. Okay, there's only one force acting on it, opposing motion. Motion is in the forward direction. So net force is just a frictional force. That's it. It should be 8,000, not 800. It's just being careless there. So I'll make a correction shortly. And then the acceleration is caused by the net force. All right, so this is 8,000. So the mass of the car is 2,000. So I made the correction. So it's 8,000 divided by 2,000. So it's going to give you 4 meters per second squared. This is tremendous amount of acceleration at this point. I mean, the car literally, I didn't have to put the brakes on, but it just slowed down significantly. Okay, now decision time. So formula would you use and why? Okay, T is what you're looking for. The formula is T in it, so it's this one and so is this one. Got 3 options. Okay, you can use this one, assuming that this is jerking motion, which means that you have a variable acceleration. So somehow the engine breaks down and then the car jerks to a stop. All right, then use this one. If it's a smooth stop, if the acceleration is uniform, then you have to use these two. Those are the options that you have. You know the distance, you can figure out the time, so that's a viable option. Except this is T is squared, so this is a quadratic equation that's going to require a quadratic formula. So that's a little bit of math. If I can avoid it, I don't want to do it because I'm lazy. So I'm just going to focus on this one, check to see if this works. I know the car is moving. It's got an initial speed, 73.5 miles per hour. It'll stop. And I know what the acceleration of the car is. That's about 4 meters per second squared. So T is the only one which is needed. So that's the one that I decided to use. For algebra, if you got zeros, for symbolic algebra, use them. It's going to simplify it. Let's solve for A. So you guys are engineering students, so you know how to do this. So let's skip to the next step. All right, now let's check to see if we got everything. We know the initial speed, 73.5 miles per hour, and we know the acceleration. So the initial speed in terms of metric units is going to be 32 meters something, 33 meters. Acceleration is -4. Negative divided by negative is going to be positive. So it's going to give you positive time. It's going to be about 8 seconds, so it's realistic. Oh, so that's okay. Cool. That worked out. Okay, so that was problem number 9. Problem number 8. Problem number 9. Let's go to problem number 9. It says test quality. Okay, so far the way we've been doing problems is slightly more difficult than high school level. Right. The reason why everything gets formatted and formatted and formatted and I've been testing you on formatting is because of the following. Here's the way you will be solving problems in the future, starting with this week. Notice I'm giving you the same problem, except you're not able to break it down. I give you everything. I say, what is the amount of time it takes for the car to come to a stop? Right, so I'm going to step you through a proper solution, a physics solution. First thing you need to do is just put the center of mass in a coordinate system. This is X, this is Y. Okay, so I was real tired yesterday, so I'll make a correction. So this is your X direction. This is the initial speed. Final speed is going to be 0. This is the only force acting, opposing the motion. All right, so X coordinate system, the Y coordinate system. All right, so this is the distance it's going to take for the vehicle to come to a stop. So what's the amount of time it takes for it to come to a stop? All right, one of the things that I need to emphasize, you don't have a lot of freedoms in terms of the way you do your solutions. In the way you show your solutions. You have freedoms in the way you solve problems, but solutions are going to be shown in a formatted sort of way. The habits that I'm trying to get you guys to develop are the best habits that you can have going into engineering. Okay, it's going to save you a lot of headache. One of the things is if you're dealing with vectors, make sure that you draw things out. All right, so this F, force, these are standard symbols. When an engineer is looking at, a professional engineer looking at it, you can tell what you're doing. If a physicist is looking at it, no problem, these are standard symbols. I'm looking at this, I can see the motion in the forward direction, it stops within this distance, I can see the time, and this is the only force acting on it. There's no question about it. This is just pictorially, everything that I want to see is there, symbolically. And then I see the numbers on the side. Initially, this is how fast the car is going. It's coming to a stop. All right, so these are everything that I got here. I don't want to repeat it. So we've done the conversions. Everything is good. Step number 1 is just cleaning. Make sure everything is in the proper format. Units are formatted properly for the MKS unit system. You don't have any mixed units. Engineering will allow mixed units. Just remember that it's a really, really bad habit. And if you're working for a company, the stuff that you do sometimes, it goes to the programmers. Those are the guys who punch the numbers in the wrong units. If anything that requires an automated system, like the one that they end up sending to Mars about 20 years ago, Evidently, the engineer thought that he was getting the numbers in metric units, and the programmer thought, the guidance system programmer thought he was getting the numbers in metric units. The engineer ended up giving him the numbers in British unit system, which in engineering, which is perfectly allowed. All right, and all of a sudden, boom, the guidance system had the coordinates wrong, the speeds wrong, and that's what happened. The probe ended up crashing onto Mars, basically. So that's how it ended, and that sort of stuff happens all the time. All right, so keep your units, be consistent. Don't be afraid to just get to the metric system and get back out of it. It's a good habit to develop. In science, everything in metric units. In engineering, it's like, because you guys do feel it touches stuff. And then there are traditions involved, so people do switch back and forth, and then they keep some of the units in the metric unit system, some in engineering. It's a horrible practice. All right, so I don't allow that. It's my personal choice. It's a bad habit. We're not going to foster bad habits here, so let's start breaking that. So the numbers, just make sure before you move on, just keep it clean. Everything is here. All the symbols, all the numbers, these are your initial conditions. All right, so out of a 10-point scale, what goes on here is going to be worth only half a point. Okay, just want to make sure that everything is stated, including what you're looking for, a question mark next to it, and put down the unit that you're expecting to see. So that you don't have to worry about, oh, I want to do unit conversions at some point, or that kind of nonsense that engineers usually have. I'm not going to play that game with you guys. So just stop that habit. It's not a pleasant habit. I don't like it. I teach engineering. I still don't tolerate it. Next thing is, now we're going to dive into algebra. Okay, this is where things are going to get interesting for you guys. Now you have to start justifying which formula you're using. Okay, your solution is going to be accurate to your solution is going to be sensitive to the accuracy of the assumptions that you're making. And problem solving is an assumption-based approach in reality. Okay, so you can only get very close to reality of what's going on. It's what you do is always going to be a mathematical approximation. Okay, there's no such thing as capturing reality with 100% accuracy. Okay, not mathematically, it's not going to happen. That's the reason why there are tons of mathematical methods out there, including differential equations, this and that. And you can only do an approximation. You can get very close to the solution, but capturing reality with 100% accuracy, if it's not science fiction, it's not going to happen. Okay, now we're going to make an assumption. All of a sudden, the engine breaks down. There's a force acting on the car. Will it cause vibrational motion, which means a variable acceleration? If that's the case, I want the average acceleration. So that's a good formula. It's got P in it that you can use. Or the engine cuts in, it's going to come to a smooth stop, which means that the acceleration is going to be constant, which means that now I'm going to be able to use that. Okay, so there's no wrong assumption here. But whatever the assumption is, you have to kind of state it. Because I will say, assuming that the jerking motion or variable acceleration, I'm going to use this, which means that these three formulas will become unavailable to you at that point. After that assumption, this is not, you put them aside, you assume that that reality doesn't exist. All right, because the solution is going to be assumption-based, and in reality, this and that, those two formulas are the same. I'm going to say, mathematically, symbolically, they're going to be the same. So I'm going to say, I'm going to assume that the acceleration is constant. With that assumption, I'm going to come up with a really good estimate. All right, so I'm going to just justify that to the one that I'm going to use, assuming the acceleration is constant. That's the only statement that I have to make. And I'm going to be ready to go. So now, assuming that the acceleration is constant, I got three options available. It's got T in it, so it's this one. For the reasons that I expressed, I can make this work, except it's a quadratic equation. I don't want to deal with that. And this is a better approach, so I'm going to use that one. Okay, just like before. Right. Problem solving is a bit of an art. Okay, it's like learning to play video games. Okay, problem solving in physics is not the same as problem solving in math. Problem solving in math is a bit of a linear process, at least in the undergraduate level. All right, so you follow the steps. There's an approach that you keep following, you get better at it. Physics is not like that. Problem solving in physics is like learning to play video games. Guys, the more you do it, the better you become at it. The only thing I can demonstrate here is the way I solve problems. You will develop your own style eventually. Okay, so you don't have to solve these problems exactly the same way I do, but at the same time, I want you to show work the way I do. It's not the same. My problem solving it's a very direct approach. I just go after what it is that I'm trying to find. Okay, so my goal is to get the T. And then I got two formulas available to me, and then I'm looking at this one, so that's the one that I'm going to focus on. I always pick the formula that has what I'm looking for in it. Okay, and then you wrestle with it. Okay, I check to see if I can simplify it. Okay, if I have any zeros, that's going to make my algebra simpler. All right, so final speed is 0. That's fine. Here's what I'm looking for. I'll just isolate it, get T on the left. As soon as it's on the left, I'll stop. Okay, the only thing I know is the initial speed. I don't know the acceleration. So what do we do? Okay, here's what you guys do, which I'm not going to like at this point. You will look for a formula that has A in it. All right, that's a mathematician's approach. That's just following the symbols, playing games with symbols. Absolutely not. You're blinding yourself. You're not able to do physics when you start to do math in that fashion. The only thing I look at is I know what A is acceleration. I know what causes acceleration. That's the force, guys. I don't have to. I know which formula I need, even if I didn't memorize it. Right. So that's Newton's second law. Acceleration is caused by an external force, and I know it's not external force. It's not just an external force. It's not external force. I know that there's only one force acting on the system opposing the motion, and then so which means that that force, force summation is the frictional force, the negative frictional force. So back substitution. So this becomes negative of the frictional force right there. Now I'll pull my A out of it. I'll do a back substitution. And so the M is the denominator of a denominator, so which means that you can pull it up. You got negative, negative divided by negative is positive. That's it. Everything that I did would be 90% of your work. It's very clean. It's very easy to grade. If there's a mistake, it's very easy to see when something is this well laid out, because it takes 15 seconds to grade this. And you got a number for mass, you got a number for speed, initial speed, you got a number for friction. You got all those numbers in metric units. It's just a one single computation at that point. And it's going to give you 8 seconds or something. You end up doing the same. All right, so get into the habit. This is the right habit to develop. If you want to be a physicist, engineer, or whatever, all right, keep everything in symbolic form. Easy to see, easy to grade. When you make a mistake, when you go back, you go, oh, I messed it up right here. So you'll know exactly what's going on. All right, weight is the force of gravity acting on a mass. That's it. So the gravitational force acting on an object is known as weight. So here's Newton's apple. When you drop it, it accelerates because there's a force acting on it. That's it. So force causes this mass to accelerate, right? All right, so the acceleration is going to be the same as g under the influence of gravity. All right, so A turns into a g, so mass times the gravitational acceleration is known as weight. So the gravitational force acting on an object is known as weight. So the measure of gravity becomes weight. W is your weight, M is your mass, G is the acceleration due to gravity, and that's it. Okay, so get out of it. Weight is mass times the gravitational acceleration. Okay, what is G? What's the value for G? I want to do a bit of a demonstration. At the same time, I want to be able to see what you guys are saying. Okay, so acceleration is 10, right? It goes from 0 to 10. What am I saying? As soon as you let it go, it's going to start to accelerate. Okay, so it's accelerating at a rate of 10 meters per second squared. All right, so what is weight? Weight is mass times the gravitational acceleration, right? So does this mean that this thing has weight while it's accelerating at a rate of 10 meters per second squared? Because as soon as it hits my palm, it stops moving, right? There's no acceleration in this direction. Does this mean that it's weightless right now? Okay, the reason why I'm asking this question is because while it's accelerating, acceleration is 10. When it's falling, the acceleration is 10. 10 times the mass is its weight. Now it's not accelerating. So does this mean that it becomes weightless? It becomes weightless. All right, because the acceleration is 0. 0 times 1 is going to be 0. 0 times 100 is a 0. 0 times a trillion is a 0. 0 times cannon is 0. 0 times a ball is 0. So what's the acceleration? Acceleration is 0. So does this mean that it's weightless? Okay, so 0 times mass has to be 0. So does this mean that this thing is weightless? What's your acceleration right now? It's 0. What's my acceleration right now? It is 0. So does this mean that I'm weightless? So, I mean, the mass is still there, but what happens to the weight? That's what I'm getting at. So if you're thinking that this thing became weightless because it stopped accelerating, let me tell you something, guys. Yeah, it stopped accelerating, but I can feel its weight. Okay, just because something stops accelerating, does this mean that that thing becomes weightless?
Stephen adds some more weight. He's the world record holder in the hand and thigh lift. This day he's attempting 1,500 pounds, 6 times his body weight. He clears it easily. But ever the competitor, Stephen adds some more weight. A measly 10 pounds. A clean lift will now put him in the record books. Unfortunately, he'll break something other than the record. It's a gruesome sight as his leg crumbles beneath him. The weight is too much for his
Well, just because the weight set is not accelerating does not mean that it's not weightless.
body to bear.
It's got so much weight that it ended up,
The fibula and tibia bones in his right leg snap like twigs.
his legs snap. Gotta tell you, this is disgusting.
Stephen learns a very
All right, moving forward. So just because something stops accelerating, doesn't mean that it becomes weightless. The weight is still there, right? The weight is still there. This is not a commercial. All right, so it's still there, but there's no acceleration. So how do you account for it? Given the fact that this thing is not accelerating, how does it still have weight? Where do we get the weight from? All right, the weight is still there, but it stops accelerating because the net force acting on it is 0, right? And the weight is pulling it in the downward direction, and the surface is applying a force on it in the opposite direction. This is known as the surface force. This is a reaction force. It comes about because this mass is pushing up against the surface with its weight. And so this is 90 degrees to the surface, so it's known as the normal force. Normal is not used in the sense of normal versus abnormal. It's just a mathematical term. All right, so this thing stopped falling because it hits the surface. The weight is still there. It's not going to vanish. That weight is the gravitational force that causes it to accelerate at a constant rate. It's there. That tendency is still there. The net force became zero because as soon as it hits the surface, there's going to be a reaction force acting on it from the surface. There's going to be a surface force. It's known as the normal force. It's called the normal force because normal means in mathematics, it means it's a force that's perpendicular to the surface. It's not used in the sense of normal versus abnormal. It's just the normal means it's a surface force. It's perpendicular to the surface. It's going to be a reaction force, any force acting against the surface, any force applied to the surface. So it could be your weight could be the action force. Normal force is going to be a reaction force. You may be pushing up against some kind of a surface like a wall. Okay, so the reaction force is the surface force acting back on you. So the normal force is the reaction force in that case. All right, so if you are getting a reading from a scale, it's known as the apparent weight. That's a normal force reading from a scale that you're getting. So the acceleration becomes zero along the y direction. All right, so which means that the net force on the y direction is zero whenever a falling object hits the surface and comes to a stop. All right, so which means that we have to do a force summation on the y direction. So W is in the downward direction. Normal force is going to be in the upward direction. All right, up is going to be positive, down is going to be negative in terms of the forces. So N is going to be positive, W is going to be negative. All right, so the net force is what causes acceleration. You know the acceleration on the y direction is going to be zero. So which means that your normal force reading comes from your weight. It's going to be the same as your weight in essence. All right, so if you're standing on a scale, the reading that you get from a scale is going to be your weight or the apparent weight. Okay, given the fact that the scale reading is the same as your actual weight, why do we call it the apparent weight? Does this mean that the apparent weight, the scale reading, is going to be sensitive to the accuracy of the scale? I didn't say it right, so I'm just going to go back and restate it. Can you fool the scale into giving you a different reading other than your actual weight? That's what I'm getting at. It's called apparent weight because the apparent weight can be different from your actual weight. So case in point, let's assume that you're dieting. You want to lose about 10 pounds a week, and then you manage to lose about a pound. At the end of the week, you're standing on the top of a bathroom scale. It's 1 pound, guys. 1 pound. That's reasonable. Except you were a little bit more. You were a little bit too ambitious. That's 9 pounds. You wanted to lose 10 pounds. Obviously, you got 9 more pounds to go, and you decide that you're not going to leave that bathroom unless you lose 9 more pounds. Except you're in a hurry. You got to leave within the next 30 seconds. That's it. Mind twister right there. So how do you lose 9 more pounds within the next 30 seconds? What is it that you have to do? The only thing you have to do is just fool the scale, guys. How do you fool the scale into thinking that you lost like 10 pounds or 9 more pounds? What is it that you have to do? All right, so scale is what you're trying to fool. Shit. All right, so you're just trying to create the impression that you lost 10 pounds within the next 30 seconds. So how do you do that? Anyway, so before we get back to that question. All right, so downward force, upward force, they will be equal to each other. If the weight is larger than the surface force, obviously the surface is going to either break or it's going to crush.
Hello, sunshine. Sleepy. Make room for shoes. The world's biggest shoe store is here. Nordstrom.
So you want to lose 10 pounds, 9 more pounds before leaving the bathroom, and you want to do it in the next 30 seconds. How do you do that? How do you fool the scale into thinking that you lost 9 more pounds?
Oh, 225! That means I lost weight!
Homer, you're on the towel rack.
What you need to do is display some of that weight onto something else. All right, guys, you can put 1 foot on the floor. Obviously, you're going to weigh less. Or you can put your arm on a countertop. You're going to weigh less. All right, so the apparent weight and the actual weight, they don't have to be the same. That's the reason why I'm an apparent weight. So the scale reading may not be the accurate measure of your actual weight. All right, what is it? The normal force is a force that's always equal to the weight of an object. Okay, most of you guys said B. For picking B, I'm going to give you guys 2 points. Victor, give yourself 5 points. It's a reaction force, guys. It doesn't have to be a weight. And it's not always equal to the weight of an object. It could be more than your actual weight. It could be less than your actual weight. It's just the reaction force to any force applied to your surface. All right, so A is the best answer. So those of you guys who pick A, give yourselves 5 points. Now imagine that you're inside an elevator, standing. Okay, you're inside an elevator. The elevator starts to go down. Do you feel heavier, lighter, about the same? All right, so most of you guys are light sensitive, right? Light sensitive. Okay, man, today's lecture is not working. I need to get coffee. Most of you guys are motion sensitive. That's what I meant to say. Everyone is light sensitive, so you can see in the light, but you guys are motion sensitive. Elevator starts to move in the downward direction. Do you feel heavier, lighter, about the same? And most of you guys are gonna feel lighter, right? All right, is this just the feeling that you get? Or is this really what happens if you're standing on a scale? I mean, when you look down on the scale, the reading that you get from a scale, will that be smaller than your actual weight? All right, so I created a project done by one of the Chicago students, and he had done this project in a high-rise. He's standing on a scale inside an elevator. I'm not sure why he's not wearing his shoes. No, he's not naked, or else something else would be sticking out as well. This guy weighs 240 pounds, right? So look what happens. So what do we do? An elevator is going down. So it's just going to accelerate in the downward direction initially. And as soon as the elevator starts to accelerate in the downward direction, notice that its original weight is going to jump down, almost jump all the way down to 200 pounds. All right, so not only do you feel lighter when the elevator accelerates in the downward direction, evidently you do become lighter according to the scale. And then what happens is the elevator reaches a certain constant speed, and at that point you will feel normal. All right, so the elevator is moving at constant speed. Its actual weight is 240. Scale rating is 240. Everything is fine. Now the elevator is going to start to come to a stop. It's slowing down to a stop. It's just moving in the downward direction. All right, so would you feel lighter, heavier, or about the same? You know, you will feel heavier, right? All right, so according to the scale, as the elevator comes to a stop while moving in the downward direction, you will feel heavier because according to the scale, your weight jumps up. I mean, his weight literally jumped up to 300 pounds. So we got 3 conclusions. No acceleration, no change in weight. When the acceleration is in the downward direction, you will feel lighter. When the acceleration is in the upward direction, you will feel heavier. So no acceleration, no change in weight. When the acceleration is in the downward direction, you will feel lighter. When the acceleration is in the upward direction, you will feel heavier. All right, so let's get back to the review. So fill in the gaps. So what's weight? Weight is the gravitational force acting on the mass, right? Force of gravity becomes weight. The measure of force of gravity, force of gravity acting on the mass becomes the weight of that object. So mass times the acceleration due to gravity is your weight. So how does weight differ from mass? Mass is the inertia, measure of inertia, or measured inertia, and weight is the amount of gravity acting on that mass. So what's a normal force? It's a reaction force against any force acting on a surface. It's got to be 90 degrees to the surface, so that's the reason why it's known as normal. It's a mathematical term, and that's it. What's your apparent weight? It's a normal force reading from a scale. So does this mean that the apparent weight could be different from your actual weight? Absolutely. You can fool the scale. All right. You can shift some of your actual weight to a different surface, countertop the floor or whatnot. Also, it's going to be sensitive to the acceleration of the mass on top of it. So you're inside an elevator. Question number 21. It's accelerating in the downward direction. Do you feel heavier, lighter, about the same? So you will feel lighter, right? So that's the correct answer. When the elevator starts to move from rest in the upward direction, do you feel heavier, lighter, about the same? So you will feel heavier. When the elevator is moving at constant speed, do you feel heavier, lighter, about the same? So it's going to be about the same. All right, so. All right, now let's take a look at what happens inside the elevator. Let's set up the mathematics for it. So this is your center of mass, center of gravity, center of your balance. The force of gravity is acting on your center of balance. So which means that you got some weight. You're standing on top of a scale. Scale is right there. And here's the scale reading. All right, so that's your normal force reading, otherwise known as the apparent weight. Now, elevator can accelerate in the upward direction, positive acceleration, or the downward direction, negative acceleration, or it could be moving at a constant speed or standing still. So there's no acceleration. So let's come up with a mathematical model for the apparent weight. So I'm going to sum up. I'll do a force summation along the y direction. N is up, W is down. All right, acceleration could be up, positive. It could be down, negative, or no acceleration. So net force is what causes the acceleration. All right, so the apparent weight is what we're looking for. The apparent weight in this case is going to be the normal force, N, that we're looking for. All right, so this is our formula, M minus W plus M minus MA. All right, so add W to both sides. And that's it. That's the final equation. So your apparent weight is on the left-hand side. So how much you appear to weigh depends on the acceleration of this mass. If the acceleration is in the upward direction, it will weigh more. If the acceleration is in the downward direction, acceleration of your mass is going to get subtracted from your weight, so it's going to weigh, you're going to weigh less. All right, so there are three possibilities here, so let's just go over all three. One possibility is that the acceleration is in the upward direction. So this is your actual weight. So the apparent weight is going to be acceleration of your mass larger than your actual weight. So your mass's acceleration is going to get added onto your actual weight. So that's the reading that you will get from a scale. When the acceleration is in the downward direction, your mass's acceleration is going to get subtracted from your weight, so you're going to weigh less according to the scale. Obviously, if there's no acceleration, your scale reading is going to be accurate to your weight, so your parent and the actual weights are the same. All right, so that's the mathematical model. I'm going to turn this into a mind twister, a slight mind twister. All right, so this goes back to the observation that we had the first week. Remember the guy inside the elevator, the cable snap? Here's the guy, the cable snap. All right, what if this guy were also standing on top of a scale? And as soon as the cable snaps, what's the reading that this guy's going to get from the scale? All right, so that's what we're analyzing. So what is N? All right, so at this one, I'm going to open the room, floor for discussion. How much do you think that the person is going to appear to weigh according to the scale? What kind of a reading do you think this person is going to get from a scale as soon as the cable snaps? What do you guys think? So you're inside the elevator, standing on a scale, the cable snaps, you look down, what do you see? What's the reading from the scale at that point? All right, so I'm going to give 20 points for the best explanation. This is a mind twister. So what do you guys think? All right, I think everybody's minds are kind of twisted. You're not able to figure this out. All right, no one wants 20 points. All right, so you're inside the elevator. All right, so Jordan's scale reading would be the same as Jordan because the gravity is still moving you plus the scale. All right, Jordan, I'm going to give you 5 points for that one. At least one person says that the reading is going to be the same. All right, so moving forward, let's just analyze this. So what's happening is the cable snaps. You're inside the elevator. This is your center of mass. The weight is still the same. The weight is not going to change, guys. That's the amount of gravity acting on you, right? This is the amount of gravity acting on you. So that's not going to change. It's going to remain the same. So the question is the reading. So the question is the reading that you get from a scale. What happens to it? Reading that you get from a scale is going to be sensitive to the motion of the elevator, right? All right. So what's happening is acceleration is going to be in the downward direction. So let's grab the formula applicable to that case. So which means that the acceleration of your mass is going to get subtracted from your actual weight. That's what it means. As soon as the cable snaps, what happens? Your acceleration becomes the same as the gravitational acceleration. A becomes G. All right. So this A becomes G. So mg minus mg is going to be 0. All right. So your scale reading goes down to 0. All right. So what does that mean? What that means is your center mass is not going to move. You're going to be standing exactly where you're standing. You're still standing on top of the scale, except you're not in contact with the scale at that point. All right, because you're applying no force on the scale and the scale is applying no force back on you. You will feel weightless. That's what it means. All right, you're not going to be able to feel the floor under your feet. You're not going to move up. You're not going to go down. You will become suspended. You're going to move with the elevator at the same acceleration while feeling weightless. So that's what happens. All right, this is known as apparent weightlessness. You will appear weightless inside the elevator. You will feel weightless inside the elevator. So that's what happens when you reach. As soon as the cable snaps, you will feel weightless. Okay, so remember, there's a safety system that's gonna catch the elevator, and we'll bring the elevator to a complete stop. I can't even talk. I'm too tired. All right, very gentle stop is what we are dealing with. Okay, so if you have 6 Flags there, I'm sure it's the same as the one that we got here in Chicago. So there's a giant drop. Just get in there. There's going to be an elevator. It literally goes into a free fall. And there's a safety system when it kicks in. You come to a complete stop without injuring yourself. So that's what should happen when the safety system kicks in. But this person had a broken neck. So the question is, how did they break his neck? So the investigation is going to continue. All right. So how much physics have we done within the past 10 minutes? I got news for you. None. Okay. So we made a few observations. We came up with a mathematical model that agreed with the observations. And we made it look like we were doing physics, but we didn't do any physics. How so? Guys, unless you can explain why this person feels lighter when the elevator is going down, starts to accelerate in the downward direction, It's not physics at that point. Yeah, it's related to physics, but you're not really getting to the core of the question. All right, so when the elevator starts to go down, you will feel lighter, right? So why? What's the reason for it? Don't tell me that the mass times your acceleration gets subtracted from your weight. That's not an explanation that I'm looking for, all right? That's a mathematical explanation. It doesn't really touch the spirit of the question. It doesn't really answer the question. All right, so the reason why you're going to end up feeling lighter has everything to do with the reason why your body moves in the opposite direction of the acceleration of the car. Right? The car accelerates in the forward direction, your body moves backward, right? Why? Because of inertia. You got mass. That mass is a tendency to retain its initial motion. That mass is a tendency to resist change in motion. Same thing happens here. Massive objects, they're not going to want to move if they're at rest. When the elevator starts to accelerate in the downward direction, mass, because it's got inertia, it's going to resist that change in motion. And that change in resistance is going to appear as the lack of weight in the scale. So there's going to be a deficiency in the scale that you're going to be seeing. All right, so the change in weight comes from your inertia. Elevator is moving at constant speed. What do? You have a tendency to move in at constant speed. There's no change in weight. When the elevator is slowing down to a stop, your body wants to keep on moving at a constant speed in a straight line, so there's that tendency. So your body is going to resist change in motion. As a result, the tendency is going to appear as the extra weight on the scale. So it comes from inertia. All right, I see A again. Okay, very good. So the person weighs 170 pounds. Elevator is ascending, which means that it's going up. You know it's accelerating because it's got the units of acceleration. So acceleration is up, which means that you will weigh more, right? Very good. Give yourself 5 points. Okay, I see a lot of B's here, so let's analyze. So suppose you're in an elevator that's moving upward. It's moving upward at constant speed, right? The velocity is constant. All right, so according to the scale, you weigh 600 newtons, so that's your actual weight. So you guys like B, so let's check to see if that's correct. So according to B, the scale registers a value. That's going to be equal to 600 newtons during the time when the elevator slows down to a stop. Okay, when the elevator is going up and slowing down, what happens? Guys, refer back to your own life experiences. Elevator is going up and slowing down. You will feel lighter, right? So you will feel lighter. So B is not the right answer. C is the best answer, if that's the case. Elevator is going up and slowing down. You will weigh less. That's what it is. All right, so either you know the answer because of your life experience or experiences, or you can figure out the answer from what little physics that we covered so far. All right, guys, the car is moving in the forward direction. You put the brakes on. What happens? Your body is going to move in the opposite direction of the motion, right, of the vehicle. So your body always moves in the opposite direction of the motion of the vehicle. All right, so the car is moving forward, slowing down. Your body wants to move in the forward direction. Elevator is going up and slowing down. Your body's going to want to move in the upward direction. All right, remember, elevator is going up and slowing down, which means that the acceleration is in the opposite direction of the motion of the elevator, which means that the acceleration is going to be in the downward direction. When the acceleration points down, you will feel lighter. So C is the best answer. Those of you guys who got C, give yourselves 5 points. All right, so moving forward, when the elevator starts to move from rest in the downward direction, you will feel lighter because of inertia. When the elevator starts to move from rest in the upward direction, you will feel heavier because of inertia. And lastly, when the elevator starts to slow down to a stop while moving in the downward direction, so it's going down and slowing down, do you feel lighter, heavier, or about the same? So it's going down and slowing down. It's slowing down as it's slowing down. Do you feel lighter, heavier, or about the same? The answer to that question is going to be, all right, Javier, give yourself 2 points. You will feel heavier, right? It's going down and slowing down. Once again, life experience, or the motion is in the downward direction. Because it's slowing down, the acceleration is going to be in the opposite direction of the motion, in the upward direction. If the acceleration is up, your body wants to move in the opposite direction. If the acceleration is up, you will feel heavier. All right, so the inertia is going to make you feel heavier. All right, so we're done with that.